Hey, hello. Thank you for being here. It is great honor to be presenting at Code Blue as part of U25 track. What we are going to talk about is how to fuzz Windows kernel driver using symbolic execution. Unlike other sessions, the focus will be on how to discover bug and perform fuzzing rather than on exploitation techniques. As you can see in our subject, we will introduce fuzzer that can find the vulnerability with just a one click. We will cover everything from the basic knowledge of Windows kernel driver to smart method for finding vulnerability. Before we go any further, please allow us to introduce ourselves. I am Sangjun, currently pursuing master degrees at KAIST and as a member of Software Security Lab, and I'm interested in fuzzing research. And she is Yunjin Park, a student at Seoul Women's University, and she is interested in enterprise security and red teaming.
Hello, I'm Jongseong Kim, a student at Aju University and a security researcher at NK Whitehead. Here is today's agenda. In this presentation, we will begin by explaining what a Windows kernel driver is and why automation is essential for finding vulnerabilities. Following that, we will introduce our research project, msFuzz, and demo video is also prepared. After all, summarize the vulnerability we discovered and conclude by sharing key insights. The importance of Windows kernel driver security is easy to see in the CrowdStrike global IT outage. Although the issue was caused by a bad patch, which resulted in blue screen of death. And it shows us Windows kernel driver can have a big impact, not just in digital world, but also real life. You can imagine if it had been critical vulnerability, hackers could have taken control of all the systems in the picture. In this way, Windows kernel driver vulnerabilities can unintentionally expose users to potential backdoor risk worldwide. Hackers are also aware of this, and the exploitation of Windows kernel driver vulnerabilities is on the rise. As shown in the data, case of attackers taking control of system through these vulnerabilities sharply increased in 2023, and similar levels are expected in 2024. This means Windows kernel driver secure is more and more important. However, what is a Windows kernel driver? Windows kernel driver is one of the core components of Windows run with high privileges. Kernel drivers are used in situations where applications running in user mode cannot perform certain tasks, such as directly accessing hardware or powerful control over system resource. For example, security programs like antivirus use kernel drivers with high privileges to hook system calls or perform file operations. But how do user mode applications and driver communicate? A userland application holds a handle to the target driver, which allows the application to use the functions provided by the driver. Then, how to send command? First, when the IO function is called, the IO function is in NTDLL is executed. This function uses a system call to invoke a higher level IO function in NTOS kernel. In NTOS kernel, to handle the application's IO command, a request is made to the IO manager to create the structure called IRP. The IO manager then creates the IRP structure based on the command and send it to the target driver using a IO call driver function, and the driver process the IO request. So IRP is the most important part in Windows kernel driver because driver handle the user request based on IRP structure. IRP stands for IO request packet and is a kernel mode structure that handles IO requests between Windows and drivers. And IRP looks like this image shown here and contains the pointer to a structure called IO stack location, which represents the IO stack. There are many fields inside both the IRP and IO stack location, but we will not cover all of them. Instead, we will explain which field we use to build our framework. Every I/O stack location structure inside an IRP contains a major function code, which tells the driver what kind of I/O request it needs to handle, such as open, write, read, and so on and so forth. Among the various major functions, device control routines tend to have vulnerabilities in Windows kernel drivers. Because of this, we decided to develop a fuzzing framework that specifically targets these routines. So, what is a device I/O control? It is a Windows API that allows the user send a specific command to the driver. When using this function, user need to set up an input buffer to pass data to the driver and an output buffer to receive the result of the process command from the driver. When a user sends a device I/O control request, the user's data including the input buffer and output buffer is stored in the IRP. This data is usually stored in associated IRP, user buffer, or type3 input buffer, depending on the type of I/O request. If there are no limit on the data length for the device control request, the length can be changed freely. Along with the data, the length of the buffer is also sent. These length values are found in the input buffer length and output buffer length field inside the I/O stack location structure. To wrap up this, I'll give you a simple example. When requesting an I/O command, if user send the data codeblue 2024 along with device I/O control, the user data will be stored inside the IRP structure. And the input buffer length field within I/O stack location is set to 12, representing the length of the data. Then driver receives this information and validate this length. And let's see what's going on real-world driver when validate this field. Let me give an example for this. The driver used the IRP structure to handle the I/O request, which is sent from application. And as the write function, most drivers validate this length of the data. If the length is incorrect, the driver returns an error using an anti-status value. Finally, the return value is stored in the I/O status field of the IRP. And the driver calls the IOF complicate request function to complete the I/O request. Finally, the anti-status value is changed into a system error code and returned to the user the result of the device I/O control function. The anti-status value shows whether a request in the driver has succeeded or failed. So let's take a look closer at the anti-status value. This value is important because it represents the result of the status of a system call. Depending on the success of the I/O request, a different anti-status value is stored in the IRP structure. This feature was very useful for automatically finding the limitations of I/O control code, which we will talk about later. So far, we have looked at how applications communicate with device. Next, we will explain why we choose to perform fuzzing and introduce the new fuzzing framework we developed. Today, the development and release cycle of software, as well as the amount being produced, are growing very fast. Since the volume of code has become too large for manual inspection, automating the process of checking software code has become more important. One practical and effective way to automate this is fuzzing, which has gained significant attention in software testing. The goal of fuzzing is to find bugs with minimal knowledge. There's also a fully automated fuzzing tool, msFuzz, which has shown the power of automation by finding over 30,000 bugs in 500 open source projects. That's why we decided to develop a fuzzing framework to automate the analysis of Windows kernel drivers and find vulnerabilities. So first, after looking into research on Windows kernel drivers, we saw that other researches require a lot of manual work and were not good at finding deeply hidden bugs. That's why we decided to create a new fuzzing framework. We wanted something that could find lots of hidden bugs without much manual work, and we wanted it to be effective and accurate. So, what is the challenges of fuzzing Windows kernel drivers? Take a look at this image. This is the I/O control code handling routine of a real-world Windows kernel driver. Each routine has specific sanitized conditions that must be satisfied. So this is the first reason why Windows kernel driver analysis is challenging. The second reason is that the routine handling I/O control code are quite complex. If the decompiled result appears as shown in the first image, you can analyze it quickly enough with manual work. However, if the decompiled result looks like the second image, you will need to solve very difficult math problem to analyze it. The third reason that there are dependencies between the device control routines. Remember the control flow we just saw? Well, when you have got more than 30 device control routines in there, and they are all connected with dependencies, things get super complicated. Trying to handle that chaos by hand is basically a nightmare. Now I'll hand it over to my friend Sangjun Park to introduce our fuzzing framework.
Before I explain our approach to overcoming these challenges, I'd like to show a demo video that simply demonstrates how our approach finds the vulnerability. The demo video demonstrates fuzzing on Windows kernel driver of EDR solution. Even without extensive and expert knowledge of the driver, we were able to successfully identify a stack overflow within just a few seconds. To do this, we identify the constraint and global variable dependencies of the driver using symbolic execution. In our analysis, there are 28 IO control code. As you can see in demo video, we get each IO control code constraint. Then we use this information during the fuzzing stage. So now we start fuzzing target driver. QEMU is currently booting for fuzzing, which may take some time. If you wait a couple of seconds, just trust me and keep your focus on our demo video. Oh, there is a crash. After finding the crash, we figure out the root cause based on the call stack information and such a call stack and register state. When we match the call stack offset with the offset in the IDA, we were able to quickly identify the root cause of the bug. This vulnerability was kernel stack overflow by the user being able to manipulate the argument of the sprintf function. So the point is that we were able to find the vulnerability with minimal manual work in drivers that have a lot of routines. So I will explain how to do this magic. First of all, our main goal is to create fully automated fuzzing framework for Windows kernel driver. Because identifying vulnerability in Windows kernel driver requires an extensive amount of manual work. Also, there are not enough fully automated and easy to use fuzzing framework for Windows kernel driver. In order to accomplish this, we use static analyzer that takes driver file as input. And we analyze the kernel driver with symbolic execution. We used analysis information in the fuzzing stage to generate random IRP. Finally, we made it easier to quickly identify the context of crashes when they happen. As you know, symbolic execution is one of the powerful automated approach for verifying software. And one of the important aspects of the symbolic execution approach is defining symbolic variables that you're interested in. In case of the Windows kernel driver, we set certain fields we are interested in, like buffer length, I/O status, and I/O control code as symbolic variable. Then we track the execution paths taken based on this symbolic variable for getting constraint of it. So let me give you a small example by showing how the driver handles the user's I/O control code request. As you can see in this example, the driver sanitizes a specific I/O control code and handles the user's request. By considering interesting field as symbolic variable like input buffer length, output buffer length, and I/O status, we can generate an execution tree with 7 possible state cases. From this execution tree, we need to pick one of them to find the specific constraint. For this, we prune state with invalid anti-status range to I/O status variable. And we select one of state where the I/O status field had valid anti-status ranges and find each constraint with SMT solver. Finally, we get the constraint of red block, which is needed to bigger than 1337. This process is repeated for each I/O control code. We can eventually get the constraint for all I/O control code. However, before we mention, there are another constraint called stateful. When we take a broader view of the constraint for I/O control code, buffer length is not the only one of constraint. Each device I/O control code handled by the driver can have dependency between global variables. So some code run properly after meeting this dependency, meaning there is vulnerability that only appear when approached in stateful manner. To find this type of bug through fuzzing, we decided to analyze the dependencies of all the global variables used within the control code. To do this, we analyzed the access instruction involving global variables, as shown in this code. We tracked the read or write operation on specific global variables or having global variable. They were grouped separately and later used in the fuzzing stage. Then, based on similar groups, mutations such as adding, removing, or replacing are applied only within the same group. But there is a problem that payload grow very big. To prevent the generation of excessively long payload during the fuzzing stage, we minimize the payload using data debugging. Next, I will explain the vulnerability we found after applying these mutation strategies. So this is the first example. This code had an authentication routine in the I/O control code A. If the A wasn't called, routine B wouldn't execute properly because B have a sanitized code. That means that there are code blocks that couldn't be reached through normal way. However, by considering the dependencies and mutation strategies, we were able to explore more code coverage and reach these hidden code blocks. The second interesting vulnerability was also found in real-world driver. There are 2 different control code A and B. Control code A have a buffer overflow vulnerability in global variable. Because A can copy the user buffer to global buffer without length check. And control code B have a routine that uses function pointer in global buffer. So basically, control code A and B should use independent global variable. To be more specific, control code A write value to global buffer to 711E0. And control code B read global variable as function pointer at 71650. However, exploiting a buffer overflow in control code A, we can override global buffer to 71650. So if A is followed by in B in sequences, B will reference an incorrect memory address, and it caused a crash. So we were able to discover this vulnerability by applying the sequence mutations method, which is called both stateful vulnerability that need IRP sequences. These kinds of vulnerability couldn't find and capture properly in other fuzzer without precisely considering dependencies. This vulnerability was found in antivirus kernel driver, and the buffer overflow allowed kernel's RIP controls. After finding the crash, there are some annoying issues to handle unique crashes. There are so many duplicated unique crashes that have same root cause. This is because bitmap hashing tends to consider even slight variations as unique crashes. As a result, bugs with the same root cause can be classified as different unique crashes. These drawbacks are particularly amplified when attempting to reproduce crashes in Windows kernel driver. This is because debugging a crash basically requires emulation through a virtual machine. Furthermore, each crash requires reboot due to the blue screen of death. And this makes me really annoying. As you know, manually categorizing and filtering these crashes is extremely exhausting for testers. So we want to automate this process. So for this, when a crash occurred, we capture the context, including the call stack and registers, to host OS for reporting purposes with hypercore. While analyzing the crashes we found in the Windows kernel driver, this information enabled us to identify numerous duplicated crashes, which saved us a significant amount of time. So to wrap up, we want to implement a fully automated for fuzzing Windows kernel driver. So when identifying vulnerability in drivers, we began by recognizing drivers installed within the application. Then conduct static analysis to know constraints and dependencies for leveraging high code coverage. Utilizing this in fuzzing stage, we can find even stateful vulnerability. Furthermore, when crash was detected, we can quickly identify the root cause of it. As a result, we can create a fully automated fuzzing framework that enables everything from bug detecting to root cause analysis. Lastly, when we implemented symbolic execution, we used the Angular framework to get path constraint and global variable dependencies. On top of the next fuzzer, we were able to get coverage with IntelliPT and able to do snapshot-based fuzzing for detecting stateful vulnerability. As a result, we found over 100 unique vulnerability and various types of bugs in many vendors, such as Microsoft, AMD, Mitsubishi, and so on and so forth. And got several CBs. So the interesting point is that vulnerability have been found not only in personal desktop users, but also in drivers used in industrial purposes. So lastly, we believe that there are several interesting directions for future work. First, we occasionally encounter accuracy issues with path constraint due to path explosion during the static analysis phase. Second, if we can emulate actual devices, we believe it would significantly expand the attack surface, allowing for further fuzzing opportunity. Third, because some drivers are loaded only under specific conditions or actions, if we successfully capture loaded context, I can expand the attack surface. Lastly, in order to find more stateful bug, utilizing an incremental snapshot approach could help uncover deeper vulnerability. In conclusion, we developed an automated fuzzing framework for fuzzing Windows kernel driver, which enabled us to discover a lot of bugs. If you're interested in, you can visit our GitHub repository. Lastly, especially thanks for our co-worker Byung-Young Kim, Seung-Chan Kim, Yul-Gon, and our advisor Jin-Ho-Jung, Ju-Sen Kim, Yo-Han-Won. So this is end of our presentation. Thank you for listening our talk.
はい、ありがとうございました。では、お時間がちょっとありますので、会場内からご質問があれば、皆様お受けしたいと思います。スタッフの方がマイクを持って、伺いますので、挙手いただければと思います。皆様、いかがでしょうか。今上がりましたので、今、マイクをお持ちいたします。
Thank you for the presentation. I have a question about the symbolic execution. I think you used the anger to solve the constraints, and to find the constraints, you searched for you checked the status code, right? So you checked if the status code is success, right?
Right.
But usually after the driver checks the I/O control code and returns the status code, there are hundreds of instructions to execute, which depends on some API calls, like communicating with the actual device, which cannot be emulated using Anger. So how did you handle the communication or instructions or APIs that Anger cannot execute?
We just depending on Anger framework implement, and if there is another API code that Anger did not simulate that API, we didn't successfully find that constraint.
Okay, thank you so much.
Hi, thank you for your presentation. I have a similar question about Anger and finding constraints. Like you find the IOCTL handlers by using emulation, but do you handle only the classic drivers or WDMF also? WMF.
We just focusing on WDM driver. So the future work will be expand this approach to the WDF driver.
Thank you.
Do you have any more questions from the audience?
Thank you for your presentation. How much does the sequence level mutator improve performance compared to the baseline fuzzer? So have you conducted a comparative evaluation?
There's not other prior work, so we just finding bug and just evaluate some coverage. So we have not other comparison baseline.
Okay, okay, thank you.
We still have time for questions. If you'd like to ask a question, please raise your hand. Okay, it's a little bit early, but we are going to close. Thank you very much for the presentation. 発表ありがとうございました. Just one more question.
Thank you for your presentation. So one aspect you mentioned is the global variable as a dependency. Like that part of an analysis, do you have a keyword or like reference something you could point us to, or like do you figure that out yourself? Is that a very common thing when doing the symbolic execution, etc.? About the global variables as dependency, that part. Like you're comparing the hash of something, right? Global variable, and you divided those different code part to different group.
Right.
Like that part, did you have any reference, or did you figure everything out yourself? Is that?
We just follow the reference code. Yeah, just same global buffer or having global buffer.
Is there is this a specific research topic, or like is there anything you get the idea from, or you figure it out yourself?
It's our idea, no reference, I
okay.
think.
Thank you.
Yeah, our original.
Thank you very much.
We still have time if anybody would like to ask any questions.
Thank you for your presentation. I have one question. This your mechanism, POC is Windows kernel driver only, right? How do you think other operating systems such as Mac OS and Linux?
We just interested in closed source, such as Windows. So that is very fascinating to us. So I think there is another room for improving in other Linux or BSOD and other applications, I think.